Hey, in this video, we're going to address the question that's here on the screen. How can we represent the entire universe in a single diagram? Before we jump into that, though, I want to make a couple definitions. First is, what do we mean by a linear scale? By a scale, in this context, I mean like a number line. And this is a linear scale. This could be like a ruler in inches, and you have a 0 mark and 1 inch, 2, 3, 4, etc. Now that's as opposed to, or in contrast with, a logarithmic scale. In a logarithmic scale, each unit, each tick mark on the ruler, you're not adding a fixed number, you're multiplying by a fixed number. On the linear scale here, we're adding, 0 plus 1 gives you 1. 1 plus 1 gives you 2, plus 1 gives you 3, plus 1 gives you 4, plus 1 gives you 5. For a logarithmic scale, we're multiplying. And it doesn't have to be 10, just like for a linear scale, it doesn't have to be that you're adding 1. But for this example, it's 10 is the factor. And so 1 times 10 gives you 10. Times 10 gives you 100. Times 10 gives you 1,000. Times 10 gives you 10,000. Times 10 gives you 100,000. Times 10 gives you a million. And we can also express this as powers of 10, where I'll go backwards this time. A million is 10 to the 6, 1 with 6 zeros after it. 100,000, 10 to the 5, 10,000, 10 to the 4, 1,000 is 10 to the 3, 100, 10 to the 2, and 10 is 10 to the first power. And 10 to the 0 power is 1. In fact, anything to the 0 power is 1. So anyway, just real quick definitions here. A linear scale, or linear number line, if you will, and a logarithmic scale. Now here's just a quick understanding check here of these ideas. For the linear scale here, I've extended the scale, and I'd like you to think about what would be the value of x on this linear scale and what would be the value of w. And then for the logarithmic scale, what is the value of y expressed in both ways, written out or as a power of 10, and what is the value of z. So please pause the video, think about this, and then come back. And now that you're back, I'm hoping / assuming that for x you are thinking 7, okay, 1 more than 6, and then for w you're thinking -1, 1 less than 0. And then on the logarithmic scale, your y, well, it's almost easy. It's easier to think of it as a power of 10. We had 10 to the power of 6, so this y must be 10 to the power of 7. And another way of saying that is a 1 with 7 zeros after it, or 10 million. And then over here on the left-hand side, the z would be 10 to the -1, 10 to the power of -1. Remember, a negative exponent means 1 divided by 10 to that power. And so 10 to the power of -1 means 1 over 10 to the power of 1, 1 over 10 in this case. So it would be, so we would write either 10 to the power of -1 or 0.1, 0.1 or 1/10. Okay, so that's just a quick little practice here. Now, let's do now apply this idea. Now, what kind of scale is this? What kind of number line is this? Is this linear or logarithmic? And I'm presuming you're thinking that it's linear. We're just adding 1 for each little tick mark on the ruler here. And now what we're going to do is we're going to place objects. This number line is diameter in inches. We're going to place objects here. So point to the screen, not that I can see, but for yourself, I want you to commit to an answer here. And of course, there are small apples and big apples, but where would you put an average apple on this diagram? Think about it. And I put it right around 3 inches. I don't know, 2.5, 3.5, 2 or 4, somewhere in that middle of this. Apples aren't, they're usually bigger than 1 inch. And they're not as big as 6 inches. So somewhere in the middle, you have it anywhere there. Where would you place a grapefruit? Well, again, they're different sizes of grapefruits. I place mine, a little shy of 5 inches, and again, I don't want to quibble over exactly where you put it, but I presume you put it to the right of the apple. Grapefruits generally are larger than apples. And what about a raisin? What about a raisin? Where would that go on the diagram? I put it here, a little less than half an inch, maybe 3/8 of an inch or something like that. And so let's think bigger. Let's think bigger. Now we have diameter in kilometers. And again, my question to start off with is this a linear scale or a logarithmic scale? And it is, in fact, a linear scale. I'm not adding 1 on each tick mark. I'm adding 2,000. So we go from 0 to 2,000. Plus 2,000 gives you 4,000. Plus 2,000 gives you 6,000. Plus 2,000 gives you 8,000, etc. And what we're going to do here is we're going to place, just like we did with the apple and the grapefruit and the raisin, we're going to place planets. So where would you place Earth here? Where would you place the moon? Where would you place Mars? Now, I don't expect you to have the diameters of different planets memorized. Here's a little graphic. The Earth is 12,700 and something kilometers. Mars, just shy of 7,000 kilometers, and the Earth's moon about 3,500 kilometers. So if we go back to our number line, our linear scale, that would place the Earth about here. That would place Mars about here, and the moon there, and then Mars is in between. So now my question to you is, on this number line, where would you place an apple? So you could have the planets as well as fruit. Well, think about it, and I'm assuming you're thinking, gosh, they're going to be over here right next to the 0. Is it technically exactly 0? No, but the diameter of an apple measured in kilometers is going to be a number very, very close to 0. And a grapefruit, where's that going to go? Well, it's going to go right there. And a raisin is going to go right there. So they're going to be right on top of each other. So it doesn't really work. And this is where we are going to use a logarithmic scale instead to get the fruit and the planets on the same diagram. And here is a logarithmic scale, diameter in kilometers. Remember, kilometer means 1,000 meters. So 1 here is 1,000 meters. That's about 6/10 of a mile. And then, so we're going, and we're going by tens here. So 10 to the first power, 10 to the second, up to, 100,000 kilometers. And then fractions of a kilometer. So 0.001 is 1/1000th of a kilometer. 1/1000th of 1,000 meters is 1 meter. So this is 1 meter here, roughly a yard, if you're more comfortable with that. And so Earth is going to go here a little bit, it was 12,000 something, remember? The moon was here, and Mars was in between. But on this scale, we can now put an apple. So this is 1 meter. 1/10 of that is 1/10 of a meter, or 10 centimeters. And 1/10 of that is 1 millimeter. Or sorry, 1 centimeter. 1 centimeter, sorry. And this would be a millimeter. And so an apple would go here, grapefruit would go there, and a raisin would go there, a little bit less than a centimeter. And so here, and notice they're not on top of each other. And so we've got planets and fruit on the same number line, on the same logarithmic scale. That's what a logarithmic scale buys you. And where do you think you would be as a human being? Where would you place yourself? I don't have a marker on this, but where would a human being be? Give it some thought, pause if you need to, and hopefully you're thinking somewhere right around here. That's where a person would be, maybe around 2 meters or so, a little bit less for most people. And so that's a logarithmic scale. Now let's turn around and address our original question. How can we plot the entire universe? Well, we're going to use a logarithmic scale. And this diagram is in fact a plot of the entire universe, or representative objects on all scales in the universe. And the scale, the number line, is running vertically, not horizontally. On the side here, we have distance from the center of the Earth. So it's always distance from the center of the Earth. And on the right-hand side, it's measured in Earth radii. And so you see this solid line here, and it's right by the 1. Well, that's the Earth's surface. And the Earth's surface, by definition, is 1 Earth radius from the center of the Earth. And here's the interior parts. If you've heard of the core of the Earth, the mantle of the Earth, that's what these boundaries are here. But this thick line is the Earth's surface. And then these couple of these dots here, there's Hubble Space Telescope, the International Space Station. All these green dots here are satellites in Earth orbit, in low Earth orbit. By the way, the left-hand side of the diagram is distance from the center of the Earth in kilometers rather than Earth radii. So I'm going to pan up here in a moment. These are geostationary satellites. These are the higher orbiting satellites around the Earth that are used for like weather satellites, so they're always looking down at the same spot on the Earth. So let me pan up, and the right-hand side on the scale here is always going to be measured in Earth radii. So the moon, for instance, is at about 60 Earth radii from the center of the Earth. And here's some space probes that are out in the solar system way beyond the orbit of the moon. And this here is, what is that? That looks like 1,000,000 kilometers. And then we actually shift unit here. See how it goes from 1,000,000 to 0.1? We're actually shifting units into astronomical units, AU. Remember, an AU is the average Earth-Sun distance. And I'm gonna pan up here some more. And I accidentally reset to the beginning. So here we go. We're going to pan up again. And now here's Mars, Mercury, the Sun, and the right-hand side, always in Earth radii. But over here, here's a 1. Remember, I said that this was now changed to astronomical units. The actual label is off the top edge here. But 1 astronomical unit is the distance from the Earth to the Sun. And then we've got these other planets. All the little dots here are the asteroid belt. Remember all those asteroids between Mars's orbit and Jupiter's orbit. And then here's Jupiter itself, Saturn. And here's the label, by the way, that we're now in astronomical units on the left-hand side. And the outer planets, here's the Kuiper belt. These are objects out beyond the orbit of Neptune, Pluto being one of the larger ones of those. And going to continue the pan up in the diagram. We have this region here beyond the solar system where there's not a whole lot of structure in the diagram because space is really, really empty. And so I'm going to pan up again. And we're still on the left here in astronomical units. This is 10,000 astronomical units. Going to pan up. Here's 100,000 astronomical units. But notice, oh, wait, we went from 100,000 to 1. This is another change of units. So on the left-hand side, the units have now changed to something we haven't actually talked about yet called a parsec. A parsec is a unit about 3 light years, 3 times longer than a light year. And on the right-hand side, we're still using Earth radii, so we're being consistent on the right. And this is 10 to the 10. 10 to the 9 is a billion, so 10 to the 10 is 10 billion Earth radii. And we're in the realm of the closest stars to our solar system. And there's some stars you may have heard of: Vega, Alpha Centauri, Sirius, Arcturus. These are bright stars in our nighttime sky. I'm going to pan back up again. And these are now more distant stars. We're talking about 100 parsecs here. And I'm going to pan up again. These are different nebulae. So we're now in the realm of fairly distant things in the Milky Way galaxy. Pan up again. This dotted line is showing you like the edge of the Milky Way galaxy. And now, here, the units have shifted again on the left. The units are in kiloparsecs. You're starting to see the beginning of the label there, kiloparsecs. Kilo means 1,000, so these are units of thousands of parsecs. And these, this label local group, these are galaxies. Now each of these items is a galaxy, but relatively nearby galaxies. Relatively nearby galaxies. Going to pan up once again. And now we're getting into the realm of faraway galaxies. And here's a famous one called the Whirlpool Galaxy that's really cool to look at. And pan up one more time. And we're now in the realm of the most distant things that we can even see in the universe or detect. And so what I'd like to recommend is that you rewind the video a little bit and actually study all the different labels. I didn't want to stretch this video out any longer than it already is, but there's a lot of details that I kind of skipped over. So back up the video, pause it at interesting places, and look at these different labels. And these are all things that will get mentioned at some point later in the course. So this is a very technical diagram with the scales and the numbers and everything. I'm going to leave you with a more artistic rendering that nonetheless takes advantage of a logarithmic scale. So this is a painting with the sun at the center, and then a logarithmic scale used radially from the center to the edge of this circular painting. And so we have the sun, we have some, a nearby comet, near the sun, Mercury, Venus, Earth, and the Moon, Mars, Jupiter. So the solar system, and then outside that ring, we sort of have this realm of the nearby stars, and then the further stars, and then the nearby galaxies. And then moving in, as we move further and further, each square centimeter on the painting is representing more and more space. That's what a logarithmic scale does for us. And so that here it's like that top part of that other chart that I was showing you. So this is a artistic use of a logarithmic scale that I think just makes a really interesting work of art. So that is the distinction between linear scales and logarithmic scales. Logarithmic scales allow you to get a huge range of numbers onto a manageable length of a ruler or number line.